Thanks for coming. Sorry about the technical issues. So what I want to discuss is some very ongoing work that I've been able to do courtesy of the Make Our Planet Great Again with colleagues at IPGP and various other institutions in France and in the US. And this is kind of a basic understanding of a longstanding question in hydrology and geochemistry about the variations in water with hydrology. This is a question that's been around for quite a while, but nevertheless, it's still with us. And so some new developments in the field make this a question that we can think about addressing in new ways now. And the MAPCA program has made that possible in exciting ways. So I want to talk a little bit about the critical zone, which is a concept that emerged in the last couple of decades. It's been quite useful. It's kind of a term for the reactive boundary layer of the Earth's surface, is sort of roughly defined to go from the top of the permanent groundwater to the top of the vegetation canopy. And this is where terrestrial life is almost entirely hosted. All sorts of processes go on there that involve water, the interaction of water with the mineral substrate, with the ecosystem. And so the critical zone processes are many, and the concept of the critical zone is that we need to consider these together in order to really understand the system. And so the critical zone, in some senses, has just simply been an organization of thinking. Within the critical zone, we can define, usually on a topographic basis, watersheds, and watersheds can take a whole variety of shapes and sizes. The one on the left is a dramatic watershed in the island of Hawaii, very easy to define topographically, relatively undisturbed. The one on the right is an agricultural landscape, but it's also part of a watershed, and clearly it's been disturbed substantially. Watershed processes watershed is a useful landscape organizing unit, and so we're going to use that. It's commonly used. And then we think about some kind of longstanding observations in hydrology and hydrochemistry. These two are hydrographs from two different places in the Mississippi River drainage basin. The one on the left is a medium-sized tributary of about 6,000 kilometers called the Embarrass River in Illinois. And the blue line is the discharge, and the scales are logarithmic. The right diagram is the Mississippi River at Baton Rouge, Louisiana, almost 3 million square kilometers. And the thing that I want to point out here is that the variability from the minimum discharge to the maximum discharge over the last 20 years is almost a factor of 300 in the smaller system in Embarrass, and it's less than a factor of 3 in the lower Mississippi. So small watersheds show much more temporal variability, and that variability roughly scales with basin area. When we look at the chemistry of what's in the river, we get a different result. And here we're looking at the discharge again for the Embarrass River, and on the right we're looking at the specific conductance, which is a measure of it's a simple measure of solute load. And it turns out, although for this year, this past year, the mean daily discharge varied by about a factor of 50 in the river, the specific conductance and measure of chemistry only varied by less than a factor of 3. So it's not uncommon that the solute load shows much less variation than the discharge, but that's not always the case. So the concentration discharge relationships can vary quite a lot. And one of our goals is to understand that, because we want to know, are we going to see big changes with changing climate and changing hydrologic forcing and more extreme events, or are we not? And what are the reasons for either of those outcomes? So this is a diagram that's a little busy, but it shows data from the Rio Icacos in Puerto Rico. And the reason I use it is because the USGS team that did this was very brave, and they went out in a hurricane, and so they got a very wide range of discharge. Discharge here ranged from about 1 millimeter a day to about 1 meter a day, which is an incredible amount of water. And the fact that they were able to get data during that, it's a wonder they didn't get themselves killed, but they managed to survive. So we have a wide range of discharge, and then, as you can see, a range of concentrations. And so for a number of the rock-derived elements, calcium, magnesium, sodium, silicon, we see that the concentrations in general decrease with increasing discharge. but they don't follow what we'd consider a perfect dilution curve. In this log-log space, that would have a power law slope of -1. That's the black diagonal line in all these diagrams. So even the rock-derived elements don't show perfect dilution, they show some. If we look at something like nitrate or sulfate in this system in the middle, both of those are roughly what we call chemostatic. They show little variation with discharge. If you look at dissolved organic carbon down in the bottom, or especially suspended sediment on the right, we see actually a positive relationship over most or all of the discharge variation. So the export of those materials scales quite strongly with discharge. So we get a range of different behaviors, and ideally we'd like to understand them because these matter. Here's an example of one reason why it matters. This is the data on nitrate and nitrite from the Embarrass River in Illinois, the same one we looked at over the last 20 years. And here you can see that the nitrogen content, and this is wonderful USGS units of pounds of nitrogen per day. I don't even know how to convert those to anything else, scaled against the log discharge. And you can see it has a very strong power law positive slope of about 1.5. And so if you look at the diagrams on the right, basically is that the high discharge events dominate the nitrogen loading to the system. The high discharge events account for most of the nitrogen and almost all of the dissolved reactive phosphorus. So this has big impacts on nutrient loadings, which then affect water quality and ecosystems downstream. Remember, this is a heavily agriculturally impacted catchment. So a lot of this nitrogen is coming from fertilizer use. Here's an example of how this works in a highly modified landscape. One of the critical zone study sites in our network is called IML, the Intensively Managed Landscape Site. It's an extremely flat area in central Illinois with the topographic high point of the highway overpasses. But there's about 200 kilograms of nitrogen per hectare added each spring to the fields there for corn and soybean production. And these systems, like many other systems in Europe, Western Europe, on the upper Midwest, they have many millions of kilometers of drain tile or pipe are installed beneath the fields to get the water out of the fields early in the season to extend the growing season. So we apply heavy nitrogen fertilizers to the field. They end up quickly infiltrating. Some of that goes into the drain pipe. The drain pipe then goes into a ditch network. The ditch network then quickly is delivered to the stream. And so this rapid transfer of water and nutrients from fields to streams prevents some of the natural processes like denitrification from moving that nitrate. And so something like 1/3 of the nitrogen applied to the upper Midwest Mississippi watershed actually is exported each year. And these seasonally high nutrient loadings, combination of the fertilization and the very strong positive response to discharge, have big impacts. One of those impacts is illustrated here on the left. That's the Gulf Coast dead zone, where seasonally, and this is near the mouth of the Mississippi, that's the crow's foot delta you're seeing in the top panel, and the water is advected to the west to some degree. And that high nutrient loading drives eutrophication, hypoxia, and we end up with thousands of square kilometers, more than 10,000 square kilometers typically, of the Gulf Coast becoming anoxic every year, which is not a natural result. And there are many other water quality impacts on municipalities. They have to spend extra money to treat their water, their public health issues, all that kind of stuff. Another thing with flood events, and when we talk about extreme events, is the picture on the lower right is an aerial photograph of a hog farm, an industrial hog farm in North Carolina after Hurricane Florence. The pink pond is where the waste, it's the waste lagoon, it's full of hog waste. And of course it flooded, and more than 100 of these flooded and released high nutrient pollutant waste to the watersheds during that hurricane, as did coal ash, fly ponds, chemical plants, or a whole bunch of impacts from these high discharge events. So those are special class of categories, the catastrophic floods, but even without that, we can see major events. So we want to have some idea of how these concentration variations in streams arise. And we can kind of think of two basic hypotheses that are not exclusive to one another. One is that as the water level in the watershed changes, we go from, let's say, groundwater feeding base flow, and the soils are relatively dry, and we wet it up, and we can saturate those soils. And so as we wet up the system, flow paths may take water through zones with different chemistry, different mineralogy, et cetera, that were not active under drier conditions. And so the two different flow paths can have different materials reacting to yield different compositions, and then they can mix to give the variations that we see in varying proportions. So that's certainly a possibility. We have evidence that that's certainly important in some cases. The other is the time scale. Waters entering the watershed can have very different transit times. Since chemical reaction in these systems is often a function of residence time in the system, then the variable reaction time that's available can generate variable compositions. So that's another way we can generate variability that we see at the exit as a mixture of water with different transit times as they come out of the system. So these are pretty simple ideas. So this problem should be relatively simple, right? Shouldn't be that hard to solve. Well, it's been hanging around for a while, so it is a problem that's hard to solve. On the right-hand side, so basically the critical zone is a kind of nonlinear biogeochemical and hydrologic reactor for both reactive and also for non-reactive or conservative species. On the right are some non-conservative solutes measured in precipitation, watershed that I'm currently sitting in at Cornell University. And we can see that we bring in rain chemistry, one kind, relatively dilute. That water enters the watershed. The water exiting the watershed is not only substantially more concentrated, but a very different composition. So there's lots of reaction going on in the watershed. It makes sense. When we look at non-reactive or what we call conservative solutes like chloride or deuterium, there's a very interesting study from a number of years ago from Jim Kirchner and colleagues looking at casting this in the spectral domain. And if you look at the spectral power in rainfall and stream flow, the upper panel, they're not very different. It rains, the creek rises, it stops raining, the creek goes back down. Yeah, there are some delays in there, but the overall spectral character is not substantially different. But if you look at a non-reactive tracer, in this case, chloride, the chloride concentration spectra in the rain is more or less a white noise spectrum. It's relatively flat. It doesn't depend on time scale. But when that chloride, despite the fact that it's nominally non-reactive, passes through the watershed, it comes out with a very different power spectrum, sort of 1/F scaling. And so we can see even non-reactive tracers are substantially impacted by processes in the watershed. So that can provide us information about how the system works. So there's a number of approaches to this. And the first approach I want to talk about is one that's relatively new, really, only in the last decade or so. And that, although the roots of it certainly go back quite a bit further than that, but it's been developed substantially in the last decade or so. So water entering the critical zone and eventually making its way to the stream can take almost an infinite number of pathways. And each of those pathways can have a different travel time within the system. So we have no hope of identifying each one of those pathways. Every time a worm makes a new hole, we have a new pathway, a new travel time. So the approach is to treat then the system as having a distribution of travel times and try to describe the PDF. And this can take a number of different forms in principle. So here's a diagram that I borrowed from Karen Harmon that illustrates some examples pretty well. On the left-hand side, we have a delta function, a pulse of piston flow. So new water comes in and old water is pushed out the bottom. In that case, all water exits after it's aged exactly the same amount. Relatively simple system. We could also have a system where the water is uniformly sampled from the different age cohorts in the system. And then we would get uniform and essentially a flat age distribution. That doesn't really happen much either. The third example is a gamma distribution, in this case weighted so that the new water coming into the surface is preferentially sampled relative to the old water. And so we have a bias sampling. And that kind of distribution, whether it's a gamma or maybe an exponential, which is the gamma function with a shape parameter of 1, is probably most apt for the systems that we're describing. And so a number of groups have developed ways to use a distribution function to compute what we expect the travel time distribution in the watershed. And this has been a fairly powerful approach. So here's an example. These work pretty well. This is an example of the deuterium output from a watershed in Scotland model by Paolo Benetent and colleagues. And I won't show you the whole 9 yards, but you can see that the model, which is the red line, fits the observations pretty well for the deuterium. So this is a pretty good deal. And one of the things about this is that essentially it treats the watershed as a single reservoir with a distribution of travel times within it. So it's sensitive to transit time variations, but by definition almost, it's not sensitive to spatial variability. In other words, it can't tell you about which water went on which pathway. It doesn't do that. It tells you how long it's been in there, but not what the pathways are. Also, the passive tracers they use to calibrate the TTDs in this case, such as deuterium or chloride, are largely seasonally driven variations. And therefore, we don't see back beyond a few seasons because each season looks like the next. So there's not a lot of difference over that time scale. So we have a hard time recognizing the contribution from older waters. So we need a different approach if we're going to look at the spatial heterogeneity of chemistry within the watershed. And also that often co-varies with the transit time variations. And then if we want to understand better the influence of old water. So here's a picture of a watershed. Here you can see a waterfall there in Hawaii. And here's an idea of roughly what we might conceptualize here and in other places, roughly what the subsurface looks like. So we have a soil layer at the top. We have a regolith, which is altered rock, but still contains some textural information from the rock. And then we might have fractured bedrock underneath. So after a rain event, we're going to have slow flow coming out of the fractured bedrock, which we always do. Some water coming out of the regolith. Often it travels along the regolith bedrock boundary, preferentially to some degree. And then we have relatively rapid flow in the soil and near surface runoff. So these are sampling 3 different materials with 3 different weathering histories, 3 different chemical compositions. And so in many cases, we need to worry about that. And particularly, and also that this old groundwater component is something that shows up here. So with this was really led by my former postdoc, Jean Marseille, who's at Riverly in Lyon right now. And also he worked closely with Jean-Renaud de Duzy on Rennes, his former advisor. And we came up with what we call a parsimonious 2D model that helps us calculate what these return and fast flows look like as a function of soil saturation. It helps, we can calculate storage, we can calculate groundwater flows using a Boussinesq model. And it computes the transit time distribution by using a particle tracking model. So we inject vertical particles, virtual particles, each one is tagged with an age. And when they exit, we sum them all up and see what the average is. That gives us an idea for the transit time distribution at any moment when the water is exiting the system. So this has the advantage of being able to treat stratification and allows us in principle to track old ages. There's really only 3 parameters we have to calibrate, and probably only 2 of them make a lot of difference. The disadvantage is it's computationally more expensive because you got to track all these particles. So this particular code runs in parallel. It's not something you can run on your laptop. But what we find from that is interesting. This is the Gliac catchment in Bretagne, where we did the initial work, where Jean did the initial calibrations. And so the panel on the left shows mean transit time. In the red, those are the groundwater transit times, and in the blue, that's the stream water transit times over a season. And so we can see we have some very old components in this system, which is consistent with the CFC ages. We have decadal age components in this system, and we can see strong seasonal variation in the contribution of those. And the cumulative distribution function on the right shows how at different times a year, these components contribute to the overall flow. So this is giving us a better look at both the young and about the old components in there, and also allowing us to say something about the contribution from shallow pathways, which have a different geochemical makeup than from the deep pathways. But as you might expect, the deep pathways, both the spatial distribution of the pathway, whether it's shallow or deep, and the chemical composition that the water is likely to encounter on those pathways co-vary. So that makes life a little more complicated. So if we have a picture of the water transit time distributions from either the first or second approach, then we have to convolve that in some way with what we understand about the chemistry to understand better how we're generating these differences in chemistry, how they're going to vary with discharge, and how this is going to impact water quality in the long run. And what the layperson might call water quality, I'm going to call water chemistry. People are remarkably sensitive to the taste, look, appearance, whatever they think about the water they drink. That tends to be something that pulls very strongly across all kinds of different groups in different countries. So people are very sensitive to the water that they drink. So this is something that's important, both in people's sensibility about the environment, as well in some cases being a really important thing to control. So what we find is that in general, you can show pretty easily that solute concentrations don't contain enough information to resolve these complicated systems. The variations in the concentration, even when you have detailed time series like this, are not sufficiently unique to be able to solve this sort of multifaceted problem. So we can turn to add additional tracer information. In this case, we're going to use the isotopes of some of the solutes that we're looking at. And for this example, and our current work is focused a lot on silicon for a few reasons. It's important from a geochemical standpoint. It has some advantages in terms of starting with maybe a potentially simpler solute than some others. And we have new ways of tracing it. So one of them is to use silicon isotope ratios, or in this case, the germanium silicon isotope ratio, which is sort of a pseudo isotope of the system. And here's some data from Puerto Rico, where you can see with discharge, the silica concentration at the top is being diluted and then returns, and it shows hysteresis. The rising limb of the hydrograph shows a different behavior than the falling rim of the hydrograph, in other words, after the peak flow. And then the germanium silicon ratio also changes. So during the rising limb, it follows one path, and during the falling limb, it follows another path. So that's telling us something interesting about water pathways and reactions. And also, we have to keep in mind that although we have dilution here, the dilution is a factor of several, but the increase in discharge is well over an order of magnitude. And so the flux is increasing substantially by a factor of about 13. So we're getting 13 times more silica out of the system at high discharge than at low discharge. Where's this stuff coming from? All right, that's a large change. It's not a small change. It's over an order of magnitude, and we can see that in other solutes as well. So we need to supply that somehow. So the isotope variations are useful, and in this case, I'm showing germanium silicon ratios on one side and silicon isotope ratios on the other side, just as an old schematic diagram. Notice the axes is flip for silicon because they behave sort of opposite to one another, which is convenient for us. So we take a fresh rock, which has an isotope ratio. We make secondary clays, and that's really the key fractionation step. Those clays will have less silicon-30, more germanium in them than the fresh rock, and that means the water that coexists must be depleted in germanium and enriched in silicon-30. And then as we sample those systems, either directly or indirectly to make a mixture, that shows up in the stream water. So we can have several components that contribute here, and the isotope fractionation can tell us about how those components are contributing. In this particular case, we can explain a lot of the variation we see with discharge in terms of flow path. At low flow, we essentially have base flow. We're sampling down near the bedrock interface, and that's the isotopic composition and concentrations reflect that, what we see down there. But at high flow, we're sampling from further up in the regolith as the system saturates, and we're sampling a lot of that material in the middle there that gives us those higher germanium silicon ratios, lower silicon isotope ratios. And we further can argue that roughly about half the silica in those systems is coming from quartz dissolution, and the other half is coming from kaolinite distribution. So in this particular case, the flow path variation seems to be the dominant effect, and the isotopes help us solve exactly where that material is coming from, because the system is isotopically stratified as a result of the mineralogical and geochemical stratification that was developed as the system underwent weathering. So that's a nice result. That's pretty good, and we can do lots with that in more detail, which I'm not going to go into, but that indicates that the isotopic tracers, these and others, can be quite powerful in identifying flow path variations. But We can also see variations that are related to the transit or residence time in the system. And this is some work that's really been developed by Kate Mayer and Jenny Druin to a large extent, as well as some other people. And this is an example of a homogeneous system where fluid, essentially rainwater, enters the system undersaturated with nominally zero concentration. As it migrates through the reactive system, it undergoes reaction, eventually reaching some sort of equilibrium as we go from this part of the diagram, we're reacting here, and then finally we reach an equilibrium and there's no further net reaction. So that time scale of reaction, of achieving equilibrium, depends on the fluid transit time scale and the time scale to achieve chemical equilibrium. And this is an idea that's been around for a long time, the ratio of those time scales. It's sometimes referred to as the Domkohler number, a non-dimensional number from fluid dynamics. If you're anyone in fluid dynamics, you have to have a number named after you. So this is an example of how that works. So that here the concentration changes simply because reaction progress is taking place as the water migrates through the porous media and through the reactive system. Okay, we can look at a different example. In this case, we're starting with a higher concentration and the equilibrium concentration approaches zero. And that first example was a uniform distribution, but if we put in different transit time distributions, we can get slightly different results. So here's the uniform distribution in this particular case. Here's what's known as a piston exponential distribution. Here's an exponential distribution. Gamma distributions would be a little further out here. There's not an easy analytical solution for that. So I just put the plot of the exponential. But the difference in the values is modest and maybe hard to resolve because you have to know the system in pretty much detail to be able to say, yeah, we can really tell the difference between these transit time distributions based on the concentration. So that may not be the most sensitive tracer, but one of the things that turns out, some beautiful work by Druin and Mayer, is that when they convolve the transit time distribution with the expressions for the isotope fractionation in these systems, there are really large differences because as the system migrates, as the water migrates through, we're depleting the solute, and if there's isotope fractionation associated with that depletion, we get a Rayleigh type fractionation. So in this case, we remove the light isotope, so the remaining fluid, the isotopes become heavier and heavier with time. And in a uniform case, we drive that to very high values, as with classic Rayleigh fractionation. That's the black curve. The same is true for that other sort of mixed distribution. But in the exponential distribution, the system tends to asymptote out. And the reason is we're contributing old water, which is heavily reacted, wants to go to very high isotope values, and young water, which is not very heavily reacted. And the young water, because it's not so reacted, has a higher concentration. So that young water is more heavily weighted. So that buffers the isotopic composition. So here, if we were to measure the isotope compositions, we could perhaps fairly easily decide which of these curves we were following and what kind of effective transit time distribution we were having. And all of this is in a chemically uniform environment with no spatial variation in mineralogy or chemistry or anything like that. This is simply an effect of the different transit times. So the isotopes are potentially sensitive to this, which is an exciting development. Further, up to now, we've assumed that the isotope fractionation during this process is constant. But we know that some of these systems are kinetically limited, both in terms of the overall net reaction removing solute from the system, because otherwise we wouldn't be able to see those previous diagrams. But the isotope fractionation itself can change when you go from the kinetic regime to a more equilibrium regime. And those timescales of isotopic equilibration and concentration equilibration are not in general the same. Here's an example where we did some experimental work. Nicole Fernandez did some elegant work precipitating amorphous silica at different rates. And we looked at the isotope composition silicon on the vertical axis and germanium silicon on the horizontal axis. And you can see that early on, we get strong kinetic fractionation of both, and the isotopes of silicon begin to roll over in this kind of clockwise sense and approach their equilibrium concentration down here, or equilibrium values, before the germanium silicon ratio does. So they're both starting out with kinetic fractionation, which is quite distinct from the equilibrium fractionation. but the silicon isotopes approach the equilibrium fractionation more rapidly. So early on, both of them should be disequilibrium. Later on, at some intermediate time scale, the silicon isotopes might be closer to equilibrium, but the germanium silicon ratios might continue to be disequilibrium. So with two systems, that gives us some tools to play with. So this is all pretty new stuff. And so we're using a homogeneous experimental system called the Landscape Evolution Observatory in the old Biosphere 2 system that the University of Arizona has taken over. It's a 30-meter long model hill slope with about 330 cubic meters of fresh crushed basalt on it. So it's chemically and mineralogically homogeneous, but the flow through that system is not homogeneous. And so by irrigating it with known water compositions and deuterium, Peter Troke and his colleagues are able to calculate the transit time distribution. John Chorover and I and Jenny we're in the process of sampling and making measurements on this. Jenny Druin's doing some of the modeling. And so we already see strong disequilibrium signatures in our sort of pilot data in germanium silicon, consistent with fast reaction because the basalt's very reactive and a short transport time scale. 30 meters is a big experimental system, but if we were to do this in a 1 meter laboratory column, my grandchildren would be analyzing the results because the time scale is just too long. Watershed time scales are hundreds to thousands of meters. Tens of meters is about as short as we can go and expect to get a result anytime soon. So here's a prediction of hysteresis and the isotopes. And so we haven't got enough data to see that yet, but we hopefully will see that soon. I've been getting new data even over the weekend on this. This is all developing pretty quickly. In natural systems, we finally were able to go out and do field work this summer. We weren't able to do that for the last year and a half. So here's some new data that my student Sophia collected from the Nézin Observatory in France, where we can see a discharge event where the discharge goes up and down, and we see isotopic response that we can use. And these are the kinds of data that we can use to then model the system more effectively, because we also have variations of silicon concentration and a whole bunch of other things. But these high frequency analyses, which are every couple hours or so, is something that we weren't able to do until relatively recently. So we have new models of transit time distribution, new models of reactive transport, which allow us to include the isotopes in the reactive transport models, and the ability to be able to measure these relatively boutique isotope ratios at high frequency, which is something a decade ago it just wasn't feasible. It's still not trivial, but it's something that we can do. So the high frequency sampling of both concentration and isotopes, along with the new model frameworks, make this an exciting problem and a potentially tractable problem, I think, for the first time in a while. Here's some also brand new results comparing different critical zone sites in both France and in the US and Canada, looking at the isotopic composition of silica as a function of the amount of silica reacted that we estimate, and germanium silicon ratios. Very early days on this, but what we see is these different sites are apparently demonstrating different transit time distributions. And that's interesting because those transit time distributions may be characteristic of the site architecture and tell us something a lot about that. So that's something we're pretty excited about. We get consistent results from both the germanium silicon and silicon isotope story. And this is all brand new, and hopefully this is going to be a powerful way of interrogating the effective reactive transit time distribution in these kind of systems, which then would allow us to do go quite a bit further in terms of modeling the overall response of the system. So here's kind of a summary. Thinking about what we're going to do next, these concentration discharge variations are something that have been recognized for many decades. They're important for water quality. They carry critical information about hydrochemical systems. They tell us a lot about what's going on in the system. Imagine that you're an electrical engineer. You've got a system running at steady state. You can only get so much information. So you put in a pulse function and you see what happens. Essentially, that's what we do. We look for a rain event to be a pulse function for our system so we can test the time-dependent response. And that gives us a lot more information about the way the system behaves. But these are complex systems because they integrate flow paths and flow rates, as well as chemical reaction networks. Some of those are correlated. there are a lot of wrinkles that we have to consider. This is not a trivial problem, which is why smart people have worked on this problem for a long time, and it remains not fully understood, despite the some impressive efforts by different people over many years. I think the new tools are really going to help. The new models, the high frequency time series data, they really offer us a potential to go much further on this. And I was excited when I found out about the MAPCA program, because it said, this is perfect, because this is a problem that's going to take a lot of parts, a lot of people, and some time, and the scale of the MAPCA program is allowing us to address that in a way that I think is really pretty important. The people I've been working with most closely here are listed. They're at IPGP, at University of Illinois, at University of Arizona, at University of Rennes, at Rivoli and Lyon. And all of them have at least some connection. Most of them have some connection with IPGP. So it's been really fun. I tell my graduate students all the time, if you want to work in these areas, you have to know everything, but you can't, so you better have smart friends. So fortunately, I have some pretty smart friends to work with here. So, and I would also say that, like many of you, our research was substantially disrupted by the COVID crisis. We couldn't do the field work necessary. We were limited in our ability to do lab work. So now all of a sudden we're able to do those things. It's really exciting. But for me, it was a major inconvenience and a headache. For the young people in the group and across the fields in science, it's been really pretty catastrophic. So I'm excited that we can put the young people back to work in a healthier environment. We have graduate students and postdocs who've barely been to a scientific meeting over the last 3 years, or never been to a scientific meeting because we haven't had them. So these are the things that we, as a community, and particularly the senior people, really have to be sensitive to as we go forward, because this is going to have a long-term effect on the potentially, but hopefully not too negative. But I think there will be measurable effects on sort of, the career progress of a lot of the young people in the field. Hopefully we're getting past that. We're always optimistic, but we've learned with COVID now always to hold your breath, right? But anyway, thanks for your attention. I'd be happy to try and answer any questions if I can.
Okay, thank you very much, Louis. So you can ask questions via the Q&A functionality, or also the chat, and I will then read them out. So actually, we already have one here. So yeah, Lucas, Philip is asking how your research is related to climate change. What is expected to change in 50 years from now? How can you apply what you are doing? Do you plan to use climate change projections to feed your research, or do you plan to stick with observations? So yeah.
Okay, well, no, that's a good question. So part of the motivation for this is understanding that we're seeing very clearly, I don't think I have to tell any of you living in Europe or the United States, the increase in extreme events, right? And both the really extreme events that cause sort of catastrophic disruptions that we talked about a little bit early on, but also just more intense rainfalls, even if they don't end up flooding the city. So that's going to affect we're going to see more events of that kind. We're already seeing more events, and therefore the tails of these distributions, which may have been, the 100-year flood or whatever kind of concepts, are now becoming more common. So we need to understand the response of these systems in order to do this. So I'm not a climate change modeler. I think as we develop a better understanding of this, then we can take probably not the detailed, very plot level kind of information, but we can abstract the information that we're learning and convolve it with a climate model that will predict, as many of you do, predict patterns of precipitation in the future, to understand what are the things we really need to worry about. Because there are many problems we need to solve. Clearly, we need to focus on the ones that are going to have the most impact and hopefully are most solvable. We don't want to spend a lot of money and effort solving problems that may not have much impact. So we have a range of issues here. They're ultimately, for me, I guess this is most motivated by basic science. I just really want to understand how this works. But it's clear that as a society, these extreme events, increasing high precipitation events, will be showing us more of the kind of behavior that I talked about early on in the system.
So do you also give recommendations to politics, etc., based on your research? Because, for example, you said that 1/3 of the nitrate is lost in the US in the agricultural sector just because it's, so to say, piped to the rivers more directly. Is there things that can be changed, or do you see something there?
Yeah, that's something that, I haven't been directly involved in that. There's certainly been a lot of work on the nutrient loading in the Mississippi Basin by lots of people. And it is important to make those, to provide that information to the public and to the political system, the policymakers. As you might well understand, the agricultural interests in the Mississippi Basin have not been extremely enthusiastic about the results of this kind of work, which has been, and some of the most important work has been done by people other than myself. And so there was a lot of pushback from certain sectors about, well, how well did we really know that the fertilizer use was driving these kinds of responses? And couldn't it just be sewage? And why blame the farmers when it's actually the city of St. Louis or whatever? So that when you get pushback like that, those are answerable questions in principle, and that needs to be addressed. So we have both things of very immediate public health import like that, as well as sort of longer term, how are these systems going to respond, and are they going to be able to neutralize CO2 and potentially remove CO2 from the atmosphere over different timescales? All those things need to be worked through and then incorporated in policy prescriptions in the future. Some of them are not effective on a decadal timescale. Some of them are cognizant on an interannual timescale, right? So the timescales vary quite a bit, as you know, in these Earth system models or system behavior.
Yeah, but I mean, the farmers should also be interested to know that they are 1/3 of what they put on the field is actually lost because they pipe it out. Or?
Yeah, the problem is that the fertilizer is cheap, and
okay.
You're better erring on the side of too much than too little, because in this industrial agricultural system, and it's actually not small farmers, most of these are owned by corporations and insurance companies and investment groups and stuff like that. The small farmer thing is kind of a myth in a lot of these areas. But anyway, the fertilizer is cheap, and the profit is essentially linearly related to crop yield. So the reason you get the water out of the fields early is to extend the growing season. The reason you fertilize is to get a higher crop yield. And if you fertilize a little bit too much, that doesn't cost you much. It's better than fertilizing a little bit too little. And this is true in many places where you have modern industrial agriculture. And so then trying to hit the sweet spot where you're fertilizing just enough to maintain good crop yields and not losing too much to the hydrologic system is not an easy thing to do. And so that's where these kinds of considerations about what the transit time distributions look like and how they respond to forcing are hopefully going to be helpful. But there's also going to be a battle over that that's got nothing to do with science.
Yeah.
Or little.
Okay, I have a very specialized question from Alessandro Forte. Do the probability distributions for temporal variability also reflect similar distributions for spatial scale variability? Example, does ergodicity apply?
Actually, I didn't catch all of that.
Does ergodicity apply?
Does ergodicity apply? Now, that's something I haven't thought about too much. I mean, if you look at some of these scaling relationships, they can show, you can represent some of this as power law exponents, or you can look at the, the spectral character of the output. And those are useful ways of thinking about it. But to be honest with you, I don't know if I can answer the question about ergodicity with any sort of authority. Maybe somebody else in the audience has thought about ergodicity as a better shape to address that than I would.
Well, I was just interested. Thanks.
Okay. I have one more question, and that is also related to climate change science and applicability, and that is that there's also talk about artificial weathering, that you could put basalt on fields or some olivine containing minerals, and thereby you would also be able to bind CO2. What is your take on that?
Yeah, I think that's an interesting idea. Like a lot of things for sequestering CO2. There's no one that's going to be large enough to solve the problem by itself. Pretty clearly, we got to do most of our control on the emission side, but removing CO2 with enhanced weathering is something that can make a contribution. And in order for that to be effective, these sorts of concerns, these sorts of issues will very much be necessary, because if you're going to take the time and trouble to apply some sort of amendment to the system, you need to know, whether you're applying it in the right way, the right time, and the right space, and to the right system. Because if in fact you have a system for which the surface layer transit time is very brief, you're not going to get a whole lot of reaction, and you may be wasting your time. So the question is how to apply it, how to mix it into the subsurface, how that's going to affect its reactivity is very much going to be encapsulated by these kind of issues. So I think that, some of what we see in agricultural systems is because they've been so modified hydrologically, they really have pretty different hydrologic characteristics, transit time characteristics than let's say a nearby less modified system would be. The evapotranspiration is different, the infiltration rates are different. There are literally millions and millions of kilometers of pipe underneath agricultural systems that change that dramatically. So all of those things, you got to think all of those things through before you go and spend a bunch of effort and essentially energy and money distributing amendments onto fields without knowing if it's really going to work or not. Because you might not come out ahead, you might even come out behind, because you got to mine that stuff, you got to transport it, you got to distribute it, all that's using energy, all that's contributing to emissions. So you better make sure at least you come out net zero at worst, but you like to come out substantially ahead, and that's going to depend a lot on these kinds of processes.
But would this affect river water quality?
Yeah, so it will, and so you have to be careful about that. I mean, one of the classic examples is as you change inputs to a system, you can get unintended effects. One of the classic examples is the arsenic crisis in Bangladesh and South Bengal, where in order to improve water quality, people were drinking river water with many waterborne diseases. The UN sponsored a program back in the 70s to drill shallow wells so people could drink groundwater, which has much lower pathogen loads. But it turned out some of those groundwaters had biogeochemical reactions that reduced iron and released arsenic, because Himalayan sediments have moderately high levels of arsenic in them. So they went from a problem of having high pathogen loads, lots of cholera, typhus, other waterborne diseases. They managed to lower the prevalence of those, but then something like 30 million people were affected with chronic arsenic exposure and many cases of arsenic poisoning. So you got to understand the whole system. So if you make changes to it, you have to really think it through so that you don't end up provoking consequences that are maybe not immediately obvious that result in negative water quality impacts. If in a perfect system where you just put olivine on, yeah, you're going to put a little more magnesium into the water system, you're going to change the pH a little bit, you're not going to have a big deal. But we never have such perfect systems. And so the water quality impacts you have to think through with these other things, particularly trace metals or the release of persistent contaminants, all of that might be affected by changing redox processes in the soil, for example, from adding the iron-bearing minerals to the system.
Mm-hmm. Okay, we have another question from Syed Amit Palash. He's asking, having so many global climate models in use, also many regional models, we could not really predict the flood disasters in Europe beforehand. And so what is your say on those consequences? What kind of consequences are we going to have by climate change on the cultivation system in Europe?
Well, some of that's beyond my expertise, but I would say I understand that climate models still have difficulty predicting the most extreme events, because usually those are a combination of, quote, somewhat unique factors where, let's say, two particular weather systems interact in a way that was a little bit unexpected and you get an enormous rainfall event. So I'm not so focused on those, because just like you, I'm not sure I know how to deal with them. But if we have an overall pattern of increasing high rainfall events, which we see both in data and is to some extent predicted, is reasonably predicted by models, even if it can't tell you exactly on Tuesday whether we're going to get one. I think there we can start to think about managing these systems. And Europe is largely managed, almost entirely managed watersheds, to to minimize these kinds of effects where we identify a problem that might be significant, such as nutrient loading or such as a change in redox processes that then release contaminant metals or possibly persistent pesticides in the soils, all those kinds of things. If we're just changing the calcium concentration by a little bit, that's probably going to have not so much effect. Although even there, the water quality engineers who are controlling the urban water supplies for Mainz or Paris or London or wherever it might be may have to adjust what they're doing a little bit because their processes are sensitive to pH and to the loadings for what otherwise might be benign. So in other words, if they're going to get efficient control of bacterial populations, they may have to change what they're doing some to take that into account. But for the really extreme events, I'm not sure I have an answer for that. I'm not sure that's a problem that we can really address with this approach. So at this point, because those are way, way, way out on the tails of these kinds of distributions where we have relatively little predictive power.